Now let's look at another example of how to use vector math in Maya. What I've got here is I've got a skinned head. It's basically got a bunch of these kind of joints around here that's skinned to the head and just moving it. All of these are oriented in world space though. So if I wanted to do like an animation where I tested all of these, it would be pretty annoying because I couldn't just take all of them and move them in like one direction and they would be moving nicely. So ideally what I would want is I would want them to kind of go away in the kind of direction of the head so that we would get like some nice kind of scaling effect out here so that I could see if all of them are working nicely. So we can use some vector math to actually help us do this. So first off, I've got a bit of boilerplate code here just to move these joints around. So let's just go through that. So what I have first is I've got a function that I've called push vector that basically just right now returns a vector of 1 unit in y. So if I run this code, it will basically just move all of the locators up 1 unit in y. So what I've got as well is I've got just the name of my locator here, and I'm getting the position of that locator. And I'm making sure that I go on frame 10 here because I already set a keyframe here, so I just want to make sure that I always go on that frame. And then I just loop through all of the joints that are in the scene, and for each of the joints I also get the position of that in the world. I convert that to an M vector again, and I just make sure that I keyframe the joint at that frame. Then I move, then I query the frame that I'm on. I move 3 frames forwards, and then I get my vector that I want to apply to the joint. I apply that, and then I keyframe again, and I move 3 frames forward again because basically it's current time plus 3 plus 3. Then I move it back to the original position, and then I keyframe it again. So if I just run this now, you can see basically what it does is that it just goes through and it just gives us this, so that we just have like these kind of 6 frames where we just move the joint up and down and we just go through. That's just like I found like a nice way to like just test when you have a lot of kind of controls or joints or something like this. But this isn't really nice because a lot of this might even look like it's breaking, like things like here where it's like going in, if this doesn't really look like it's working, preferably I would like to see it move out, right? So let's see how we can do that. So one very kind of simple way to do this would be to basically take the vector between each of the joints and some point in space here. So what I'll use here is I will be using this kind of locator. So really what we'll be doing is let me just turn off here and I can demonstrate with here. So let's say I'll go between these 2 points here. So what we'll be doing is we'll take this vector and then we'll apply it to the kind of current position so that what we will end up with is the vector, the joint moving away like this from the vector. So if we do that for here, I would expect this to kind of move out like this as well. So let's just go through and see how we can do that with this code as well here. So first off, what I'll just do is I'll extend this kind of push vector function here just to allow us to take in some kind of points here as well, so that or basically vectors, so that we can compare it. So I'll just say start and end. I want to say start and end here, and basically the start will be the lock position and then the end will be our joint position. So to get the vector between 2 basically points here, or the vector between 2 kind of vectors here, what we'll have to do is we always have to go to like our end point and subtract the start point. So I'll go end minus start, and that's going to give us the vector between these 2 here. And then I just return that. So if I run this code now, we can see that instead of moving up, we're actually moving away from the locator. And I can do that again by, if I move this just here, you can see that we're now actually getting a completely different, they're all moving away from that locator. Now, Oop, let me just undo that again. And let's look at a tiny bit at like how this is looking. So for most of these, it might be pretty all right. Like looking at something like around the head, but for something like this one down here, we can see that as that's happening, because this is much further away than a lot of these kind of head joints here, it's moving much further. Because really what we're doing is we're taking that whole vector and then applying it again. So any kind of joint that is like far away from the locator is going to move much farther. So let's see if we can make sure that they all move the same distance. So what I will do is I will go back into the push vector, and I will basically use I will basically take the vector and I will normalize it. So there's two ways that you can do this easily. So we can just say vec normal equals, you can say vec dot normal, and this will just return a new vector that is normalized, but it still has the same direction. Or what we could do is we could say vec dot normalize, and that would actually change the data for this object here. So that this would now just modify this data, but if we do normal, that won't modify this data. That will actually return us a new vector object, sorry. So I'll just keep this just so that we have it like each very clearly on each line here. So I'll say vec normal equals this, and let's just undo that again and go back to where we were. So now, hopefully, we should see, boom, all of these are now moving the same kind of distance here. And if I select this one again, you can see if we go here now, that just moves that 1 unit now. And the really cool thing about this now is because we have all of these vectors moving the same distance, we can now easily change and specify how long we want these to be, or like the distance of them. So we could easily kind of scale them. If we wanted them to move more, we could easily do that. So we can say vec scaled equals vec normal times, let's just say 50, just to kind of crank this up and like really see some difference here. Now, of course, again, like I said, I'm really doing this on like each line here just to like show each step, but you know, you could do this up here if you want to like do this a much in fewer lines and everything. But now we can see we have a completely different movement here, but again, they're still all moving the same kind of distance, but now 50 units, because we're basically taking the normal length here, which is 1, multiplied by 50. That'll give us 50 units. All right. So I'm just going to put this down to like something 1.5, so that it's a bit more kind of subtle. So now that we have that, we still don't have anything that's like really nice, because as we kind of talked about here, it works fairly well for like all of these ones, which are kind of in like a circle or like you know, a sphere around that locator. But for these kind of for these joints down here, you can see they're now moving like down into the geometry here, and it's not really nice to see if it's actually working nicely. Preferably I would want this to kind of move up here and more away from the surface. So another easy way that we could do to kind of extend this would be to just have more points that we're moving away from, right? So what I could do is I can take my locator here, I can move it down here, and I'll duplicate it over here, so that now we would have more points to kind of check against here. And I could do one for like here as well. Actually, I'll just remove that for now. So what we have to do now is we have to basically figure out which locator we should be using. So to do that, we can use a bit more vector math, and basically for each of the joints, we would get the vector from that joint to each of these locators. And then we would check the length of each of those locators, and we basically take the one that has the shortest length. So I'll do a new function here. I'll just say find closest. I'll just keep that very simple. And we just want to pass in a position. Because I'll just do this very simply by just having all of my locators kind of added in here. So what I'll do is we want to return basically a vector, because we'll be calculating all the vectors in here, so we'll basically just return the vector that we need. So I'll say the vector that we will just start out with is none, and then we'll start out with a distance of 1,000. Now, really what we want to do here is, I'm doing a very kind of simple way of doing this, where I know that in my kind of case here, I'm never going to have something that's a vector that's longer than 1,000. So what I'll do is I'll just go through, and for each lock, I'll say we don't even need this anymore now. So I can say for each lock in commands.ls locator, and I only have 3 of these, so I know it's going to be 1, 2, 3. So I'll just use the question mark. And what we want to do now is we want to do pretty much exactly the same thing that we did previously here. We just want to get the block position equals orm2. I'm just going to copy this. I'm not sure why I'm writing it again. And we'll take the lock here. And what I'll do is I'll make a temp vector here. So just a temporary vector that we will use to kind of figure out all of the lengths and all of that here. So that will be the, again, the kind of position. So it'll be pretty much exactly the same thing that we're doing here. So it'll be position, which is the end here, right? Because that's what we'll be passing in, will be the joint, minus the start, which will be the lock position here. So as soon as we have that, we can now do a check here, and we can say temp vec.length. We can see if that's smaller than the distance that we basically kind of specified here. So worst case, you could have, if you had like a scene where all of your kind of locators or all of your kind of points were like further away than 1,000, or something, then this would be a bit too simple. So it might be best to, instead of doing this, you could do like first check against the first locator in the list, use that as the first vector and the distance, and then you can loop through all of the other ones. But I'll just keep it like very kind of nice and clean here now. So basically, if the temp vector is smaller than the current distance, what we want to do is we want to make sure that we set the vector to be the new temp vector. I'll do an m vector here just to make sure that we get like a new clean value of this. And I'll set the distance to be this as well. Cool, and then we just have to make sure that we return the vector. And what I can do is I can actually just push this in here instead of what we had. So you can pass end in here. And that just means that we'll make sure that we do our normalization and our kind of scaling here nicely as well. So let me just double check that we don't have anything there. And let me run this. And so now, hopefully, if I select this one, we should see that it's moving away from this locator and not away from this. So you can see that's exactly what we're getting here. And I would expect to see this locator basically move from here over to something like here. And yeah, that's what we're getting there as well. So with just like a very simple kind of distance check here, you can start to get a bit more kind of nice feel to a lot of this and kind of control it a bit more. Now, this is still pretty hacky in a way because of we're just adding in all of these kind of like random points, and to make things look really nice, we would have to add in like a bunch of these probably, because if I really wanted this to move, like if we had like one joint here that I want to move away from the surface here and this to move away here, we'd have to add in like a bunch of locators, and that's going to be more kind of calculation and time to do as well. So what would be a lot nicer is if we could actually use the geometry and basically use the normals of the geometry as the vectors that we want to move along. So what we can do is we can go through and loop and find the closest normal on the surface for each of the joints that we have here. So that means that we could just get rid of all of our locators completely and use the surface normals instead, which should give us like a lot kind of cleaner thing. For a special like this one where we're seeing that was pushing out here, I would want that to kind of push up here as well. So this is where we'll have to do a bit more of the going into the OpenMaya API, which is also pretty nice. So what I'll do is I'll just keep this find closest, but I'll get rid of all this kind of locator check that we want to do here. So what I'll do is I will on here, I will actually do this outside here because we're going to be doing it a couple of times. So what I'll do is I'll add my mesh and have to do an M selection list so that we can actually kind of select this and add it in and get like all the DAG path and make an MFN mesh out of it. So I'll just do mesh dot add, and that'll be basic head. And as soon as we have that, we can then get the DAG path, which will be mesh dot get DAG path. And yeah, I'm 100% reading off notes here because I never remember this stuff. I always Google it. Basically, if you Google, just find like closest normal on mesh or something, you're probably going to find exactly the code that I'm kind of writing down here now. So obj will be om2.mfn mesh, and we will add in our DAG path here. So let me just make sure that all of that is working nicely. Cool. Because we'll be doing this over and over again, I don't want to do it inside of this kind of function here that we'll be calling for each of the joints, so I'll just do it outside. But then inside of this, what I'll do is I'll do the vector, and we can say obj dot get closest normal. And what we need to pass into this is basically going to be the point that we want to check, and then we need to pass in the space for it as well. So when I say point in the API, they actually require a point and not a vector, because this needs to be like an actual point in space. So to create a point like an on2.mPoint, all we need to do is we just need to pass in a vector that we already have. So we can just pass in position here, and then space will be om2.m space, and we'll just set this to kworld. It doesn't really matter too much for us here now because this isn't moving, it's not going around. So I'm just going to set it to that. And then what this will return, it will return a couple of different things as well, but it's the first index of this list that we really want, which will be just a normal here. So let's see if all of this works now. And what do you know? That looks like it's worked. And we can now see that this one as well isn't moving off into this distance here, but it's actually getting that normal from that surface and moving along that. And because this is actually returning a normal, we don't really need to do this kind of vec normal in here again. So I can get rid of that, and I can still add in like my scale here. If I just undo, if I run that, and we can see everything is still working as kind of expected. And we can see now that this is actually moving forwards here, and we get like all these really nice behaviors where this is moving down here now. This should be moving away here. So yeah. And then this should now be moving kind of down here. And yeah. So I found this sort of like kind of very simple code to be really, really useful. And this exact example that I'm showing here is something that I actually had to do at work at one point, where I made a similar setup like this, but to actually make the test animation for it, I had the issue where I just didn't have like a bunch of these oriented correctly in world. Honestly, I can't remember if that was an animation request or if that was just an oversight from my end, but basically I ended up having to do something similar like this. And with just like a bit of vector math, you can get some really cool stuff going here as well. And I keep finding useful needs for this, be it like creating new meshes to help me in the rigging, orienting things based off these kind of different things. All super useful. So I hope this was kind of interesting as well and that you got something out of it. Cool. Thanks.